Welcome back. I am back with new webinar number 14 on the platform of Igniting Power Engineer. This is about the testings of power transformer. What I feel is we must not die empty. We should do our bit for the betterment of society. Always be ready to share our experiences and the knowledge. We started moving towards our objective of dissemination of knowledge, and this movement was not mine, but spotted by so many legends, torchbearer, think tank, lighthouses, usher of societies, conscious keeper. I will be failing in my duty if I don't thank and mention them before I invite respected Umesh Gupta sir. I am thankful to Almighty, my family, my parents, my mentors, respected Vai Saab, K.K. Murthy sir, N.K. Mittal sir, K.K. Gupta ji, P. Ramachandran sir, S. Sapao sir, Hitesh Chauhan ji, and Dr. Kamal Bansal. And a list of my friends and well-wishers who always support me: Saket Gupta, Sanjay Agarwal ji, Arvind Tukral sir, Dr. Vikas Almari, Batra ji, CBIP. Last but not the least, my special team working day and night includes Gulab and Ramdhani. Now, time to give a brief introduction of today's speakers who is going to talk on testings of power transformer. Respected Honorable Umesh Gupta sir. Having experience of more than 28 years experience in the Indian power sectors at different location and utility, central as well as state government. He has contributed his services in all sectors: generation, transmission, and distribution. Fortunately and presently, he is the Vice President with the BRPL and the Head of Protection Department. Without wasting further time, now I would like to hand over to the respected Umesh sir to set this platform of Igniting Power Engineers on fire with insightful and wonderful presentation on testings of power transformer. Welcome, sir. Over to you now.
Thank you, Dr. Rajesh, for introducing this session, and good evening to all the participants who are with us in this session. So for next about say 1 hour, we will be discussing, and I with my team, Mr. Bharat and Varun, will share our experiences, especially related to field testing of the transformers. I would request Mr. Bharat to share that PPT. Without wasting much time, I would like to start. So next slide, Bharat. So the flow of the presentation, today's presentation will be like that. What are the components in power transformer of it, and what are the faults which may occur during its life cycle, and the reason behind these faults. Then what are different tests we may perform on the power transformer to identify or indicate these kind of problems with the transformer. Then what do different standards and recommendations say about testing of the power transformers, and that how should we test the power transformers, what should be the periodicity, etc. So then no load losses test, we will discuss the tests in detail one after the other: magnetic valence magnetizing current test, then short circuit impedance test, winding resistance measurement test. Like that we will go on discussing. We will also touch upon dissolved gas analysis, and in the last we will share some of the case studies, which few case studies out of so many we have experienced during our past 10-12 years while working in protection department and testing number of transformers. Next slide. See, in BSCS Rajdhani Power Limited, there are about 270 power transformers, and such large number of power transformers to continuously have information about their health, what are the trends, what should be the maintenance sections to be taken depending upon the uh, health analysis performed, or we draw inference from various tests. So what should be the maintenance activities, and then followed by maintenance activities again we do some tests so as to know whether the maintenance activities undertaken have been done properly, or some new trends have been emerging out after maintenance activities. And it is very critical in case of power transformer that whatever you test, you refer back these tests with respect to the your earlier recordings, so that you should compare and draw inferences about its health, or how it is how different parameters of the transformer going on. So if we talk about that core, so core during its operation, transformer operation, the mechanical deformation may take place, or sometimes shorted core laminations may be there, some residual magnetism may be there, or sometimes the grounding of the core related issues may be there. Next. Winding related issues are listed like that: short circuit between winding turns, stand to stand short circuits may be there, then open circuit in parallel stands, short circuit to ground like that. And in insulation, moisture may be there, aging related issues may be there with the insulation, contamination may take place, PD may take place with the insulation, then issues with the tap changers may be there, different kind of issues. Then lead connections, contact problems, mechanical deformation with the connections, etc. Then bushings, finally bushings, where what kind of issues may be there with bushings, aging may take place. So accordingly, different kind of testings are done to check these type of defects during operation of the transformer. So today's discussion will be mainly focused on the field testing of the power transformers. Though the power transformer testing in itself is a wide subject, and right from the factory, then commissioning and field, there are numbers of stages when we need to test the transformer. As we know that factory acceptance tests, purposes of different type of tests are different. So accordingly, we go for the testing of the transformers. But in today's discussion, we mainly focus upon the field testing of the power transformers, so as to gauge its health during its life cycle, so that different actions may be taken considering its costs, so that we should be able to enhance its life. So if we look into that, what are the different negative influences, that what are the different factors which may affect the life of the transformer, we may list out these factors like thermal influences due to overloading, overheating, then ambient operating conditions, age-related issues, means moisture may ingress inside transformer through different joints, tank openings, etc. Then acid formation, oxidation. Oxidation is again, if some leakage may take place, then that oxidation may occur at different terminations, maybe somewhere the bushing termination, then winding connections are there like that. Then contamination related issues, leakages inside of the tank. Then mechanical influences means when we transport the transformer from one side to another side, or many times when in operation due to through faults or heavy through faults, the deformation or the different kind of uh, deformations may take place because of these kind of stresses. Then seismic activities may also affect inside inside structure of the transformer. Electrical influences like switching surges, lighting surges, over voltage is experienced by the transformer during its operation time. Then short circuit currents, as I mentioned earlier also, that through faults are quite common on the transformer. These means the fault is outside the transformer on the feeders emanating from the transformer. So these are also experienced by the transformer. Then there are chances, few times it also happens that the protection which is installed maybe on our outgoing feeders or the transformer LV side may fail to operate, and the fault is cleared after some time. It may delayed due to next operation of the next line of defense protection. So that because of these reasons, the problem may also be there with the transformer uh, or its components inside winding, insulation, etc. Next. So why we need to test the transformer may be classified for the field purpose in two groups. Say one is commissioning testing. To ascertain, it is required to test the transformer whether the transformer is good to energize, whether we should put it into operation or not. So there are certain test checks which we do during or pre-commissioning, before commissioning of the transformer. Then during its operation lifetime, we do some tests. Basically, these tests again may be sometimes especially done after some events on the transformer, or maybe done routinely in routine, say in yearly. These if we do it routinely, then this purpose of these tests are to check what kind of problems or trends are going in with the components of the transformer, like insulation, health. So in short, it may be shared as the residual life assessment, RLA, aging. Then and accordingly we take remedial measures, corrective actions to to service the transformer, so that's to enhance its life, because we know that the transformer is a costly equipment, and accordingly we should keep track over its health. Next para. Next. And if we tabulate the different tests discussed in different standards. So we have, in this slide, we have tried to classify different tests in three categories. Basically, some of the tests are done routinely, and routine tests are again maybe field test or and also done at the time of factory tests. So these tests are turn ratio test. We will discuss these tests, that what are the objectives of these tests, that what information we derive out from these tests in detail in coming slides. So turn ratio test, HV and LV winding resistance test, short circuit test, PI value measurement, then oil testing, and magnetic valence test. In special test, vector group test, OLTC health check, and to know the health of the insulation, we do capacitance and tan delta test of winding as well as bushings, then magnetic circuit test, then oil testing for dissolved gases, and some special tests like frequency response analysis and frequency domain spectroscopy. Though we will not be discussing last two tests, SFRA and FDS, in this detail in this session, we will discuss sometimes later on. But these tests are also performed, especially on the transformers in field as well at the time of at factory. Then some special tests. These tests are generally may be taken as type tests or at the time of factory acceptance test. So load loss tests, no load loss tests, separate source voltage resistance test, noise level test, cooler loss measurement, harmonics measurement test, induced over voltage test, heat run test, and impulse test. So this is the this way we may classify most of the tests in three categories, and the list is not exhaustive. If you go and study the various related standards and guidelines, you will find there are so many more checks and tests to be conducted on the power transformers at different times. Maybe at the time of you accept the asset at the factory level, or you do in the field. Next slide, Bharat. So these are the standards. Generally, we consider or we go back and study while testing the transformers. As I mentioned that there are a lot of tests and checks, and if you want to study in detail, you should refer these standards and study these standards. In these standards, even the detailed procedure, detailed list, what are the different tests and what are the objectives of these tests, everything is discussed. So C57 1290 2006 is related with the standard test code for the liquid filled or liquid immersed distribution power and regulating transformers. So standard test codes, and C62 1995, which is now replaced with C57 152 2003, is basically a guide for diagnostic field testing of the power transformers. Both the documents are exhaustive documents, and it depends upon the different utilities, their practices, how they test, and depending upon their capabilities, their infrastructure, how much infrastructure they have developed according to their resources, that what tests they should perform, and accordingly different utility, the practice may vary in different utilities. Then if we consider the Indian standard, it is 2026, which is nothing but guided by the I think IEC 6076. Again an exhaustive document, and we will refer its we have referred its part 1, which is related to general definitions and tests, and part 3, which is related to insulation level and dielectric tests related with power transformers. Next. So first of all, no load losses test. It is done at the time of factory also, factory acceptance test, and also mentioned in the IS 2026, which I mentioned is like IEC 6076. So no load losses. Basically, what are the losses? Three types: iron losses, first of all, in the core of the transformer, then dielectric losses in the insulating material. As we know that every insulator has some component of losses. It is not purely insulator, so some loss may occur. So because of that, dielectric losses are there. And lastly, copper losses due to no load current. And last two are comparatively low in comparison to iron losses. So only iron losses are considered in determining the no load losses mainly. How it is done? Usually done at 90% or 110% of the rated voltage. Transformer is just disconnected and isolated from both sides. The tank is earthed. Tap is the test is performed at the rated tap. As I mentioned that these are the practices slight variation may be there if we go across different utilities, but as I mentioned that I am discussing basically what we have studied from the standards I discussed earlier, and you are practicing in BSS Rajdhani Power Limited, Delhi. So HV is kept open and AC voltage is applied on LV side. Gradually, it is increased to 90% of the rated voltage. Then in steps of 5%, and no load losses. Uh, no load losses are then measured. Next slide. It is the connection diagram. As you see, the equipment is connected with in circuit to know the specimen power transformer number, which is indicated by 6, and the testing equipment is mentioned by 5, and the connections of the CTPT connections are also indicated as 3 and source is 3. Source is 3, current transformers, power supply, and like that we connect the supply and transformer and testing equipment. Next slide. To measure no load losses. Next test is magnetic balance or magnetizing current test. Generally, it is conducted on 3-phase transformers to check basically whether the 3 windings or the 3 cores of the transformer are in balance or there are some issues. For this purpose, what we do is basically voltage is applied on one winding and induced voltage on rest of the 2 windings is measured. Voltage induced in winding depends on the respective position of the limbs, and according to the voltage distribution may take place. If we feed in the central limb, the induced voltage on the outer 2 limbs may be nearly equal, but if we inject voltage in the one side or outer limb, then the distribution of the voltage may be varying maybe 20 to 80%, and that one winding may be having 20% of the voltage and another 80%. However, the total voltage induced in the 2 windings, if we compare with the winding in which we are injecting the voltage, will be equal to the injection voltage. So the test is performed basically to detect if some issues are there in the core structure, or there are some shorting has taken place during its operation. Mainly, many times this test is also performed if we transport transformer from one place to another place. This also give some indication about the problems in the tap changer, lead connections. These conditions cause change in the effective reluctance and current required to maintain the magnetic valence will increase. Accordingly, the current will increase. So done at lowest, normal and highest steps. Comparison is done with respect to the earlier recordings, and there may be variations. Around 30% variation is allowed, permissible, but normally again there should be some trends when we compare with respect to the earlier testing results. This is a typical test table which we have performed on a healthy power transformer. You may see clearly that the voltage is injected one by one. It is a DY-N11 transformer, delta star transformer, and the voltage is injected, LT voltage is injected phase to phase in the delta winding in one by one. So as Bharat is indicated, you may see that when we are injecting voltage in one winding through terminations RY 432 volt, the total of the two voltages 366 and 66.8 volt, the two voltages should be equal to the voltage which we are injecting in the winding. Similarly, for the other two windings, the tests are repeated. But as I discussed earlier, when we inject in the central limb, the distribution will be symmetric or nearly symmetric in the two outer limbs. But when we inject in one of the outside limb, then the distribution will be say around sometimes even it may vary up to 20 to 80% depending upon the conditions. Same test is also done from the LV side. LV side again we inject because here the transfer specimen is star connected LV side. So single phase to neutral is injected in R phase to neutral. And as you see that RN voltage 240 volt is compared with the induced voltage in the two windings YN and VN, and the magnetizing current is recorded. So you may see that there is some symmetry in all the results. If we look into the results, the magnetization current is also almost similar. But if there is some problem in any transformer, as I discussed, different issues may be there, sometimes even fault may be there. So accordingly, the result will give you some insight that there is some problem has taken place inside the transformer. And you see, none of the result, you cannot say from one test that this kind of issue is with the transformer. Many times you do many tests to uh, draw inferences that what kind of problem has taken place with the transformer during its operation, maybe due to some even sometimes the problem may take place inside the transformer because of the problem or fault which was in the outside feeder. So that may also happen depending upon the conditions. Next slide. So next test is short circuit impedance measurement. Why we do it? We do it to know if there is some issues with the
Severe short circuit water may cause the winding to move.
please, somebody is talking. I would request Saket, please. So severe short, if some issues with the winding, maybe short circuit transfer with the transformer winding. So that kind of issues maybe or some deformation has taken place. This test is performed and will give some information. And it is also done to measure the leakage reactance of the transformer, which is basically is nothing but an indication of the voltage regulation, a design parameter of the transformer, whether how we have taken the design, that how much voltage regulation will take place. Generally in BSES our transformers are having percentage impedance nearly 13 to 14%, and accordingly the voltage regulation will take place. Voltage regulation is, what is voltage regulation? Drop in the terminal voltage of the transformer when you load it from no load to full load. So for that reason also, whether the designed parameter is okay or not, we do this test. So the next thing is that percentage impedance volt of the transformer. It is also indication of the leakage reactance. So it is indicated by percentage of the normal terminal voltage required to circulate full load current under short circuit conditions. Means if we short circuit the transformer during that time to uh, to inject the full load current, how much voltage will be required to be applied at the terminal of the transformer, that is the percentage impedance volt of the transformer. And how it is done? It is done by applying voltage at the HV winding, and LV winding is kept short circuited. The current and the voltage across the high voltage winding is measured. Finally, the short circuit impedance is calculated by considering the specific transformer rating. On the next slide, we will show you that what is the formula to estimate the percentage impedance. Though the percentage impedance by which we are measuring or we are estimating through this method may not be the exact according to the design parameter, but it gives approximately near to that. So the formula is indicated and the circuit is also there, that LV is sorted, one phase is sorted and what is applied in the one phase of the winding. As you see, automatically to balance the ampere turns, the current will flow in the same winding of the transformer, which you are shorting on the LT side. So if you see from the formula, the percentage Z will be equal to I rated on the LV side multiplied by V applied on the HV side divided by I short circuited, which we are measuring, multiplied by V rated. The detailed formula is given above. If you look into it, you will calculate you will arrive at the final formula. Okay. So the short circuit impedance obtained from three-phase measurement should not deviate more than 3% of the nameplate value. Next. This is these are the results of a healthy transformer. If you look into it, you see that voltage is applied on the HV winding RY with RN shorted, then YV YN shorted, BR VN shorted one by one, and the measurement is done on accordingly on all the phases LV and HV side. Currents are recorded, which you may see here. There is a pattern which you see on this table, and this information trend is in itself gives information that the transformer is healthy. If there are some issues, the results will vary and there will not be a smooth trend. There may be some variations here and there. Accordingly, we will go analyze and see that what kind of issues may be there with the even some problem has occurred with the transformer winding. Next. So next test is winding resistance measurement, which we do in field, and this is a very important test. In earlier days, as I remember when I started my career, generally the power transfer that time, these kind of tests were not there. We were testing open circuit, short circuit and Megger, insulation resistance, etc. And then charging the transformer. And many times while charging the transformer, those were the days when even the differential relay plugs were set before switching on the transformer, and sometimes even the trip command was isolated. And nowadays all these things are taken care of by through numerical relays, that when you are switching accordingly to you adopt different settings and you may avoid the tripping during charging. So this is again coming to the same topic, winding resistance measurement. This is a very important test which gives insight about the not only about the health of the winding of the transformer, but also about if there are some loose connections, terminations, bushing to winding, if there are some issues in the tap changer, and some high resistance has developed between different terminations and connections. These kind of issues may also be checked through this kind of this winding resistance measurement. Also, you to check the on-load tap changer, as I mentioned earlier. Then this test is also done to calculate I squared R losses. For this test, what we are doing is DC is injected till the current is reached to the saturated value, core saturation is taking place, but normally the test is performed below 10% of the rated current to avoid erroneous rating due to heating of the winding. Okay, next. This test is done again on every tap position. Testing the OLTC and winding together, we are kept keeping in circuit. During testing, the stabilization of current takes place, and after testing, the winding is demagnetized so that there should not be any residual magnetism inside the core, because as I mentioned earlier, the winding resistance measurement is DC test, so there are chances that and of course not only chances, the residual magnetism will remain there. And for this purpose, that nowadays the testing kits are coming with arrangement to demagnetize the core, and accordingly it is recommended that this test should be done in later stage during tested, means during last means when you have completed all other testings, AC testing, this test should be done in the last. And result, how you compare the results with the factory measurement values or the previous values which you have recorded during your previous tests, previous years, and comparison is done with respect to earlier reports, and the variation should be generally around 3% should be there, and compensation is done accordingly, because you test the transformer, you may test the transformer at different temperature, but while performing this test, it is very important that you compare the test results at the same temperature level. So whenever this test is performed, the value generally nowadays the testing kits are having this kind of arrangement that if you put the value of the temperature in the kit, ambient temperature, accordingly it will compensate for the value, and the resistance will be recorded according to the required temperature. So formula is given, though the formula has been given in the last. R new means at whatever temperature you want to convert the resistance is R new, and R old is means whatever is the measured value of the resistance. T new is the desired temperature at which you want to convert it, and T old is the at which the measurement is taken, and alpha is the coefficient. So you can always convert the resistance which you have measured at a particular temperature, you can convert it to the according to your convenience. But as I mentioned earlier, that always these values should be compared with the earlier recorded values, which is again on the same temperature. Okay, next. This table is basically test results performed on a healthy transformer. So you may see inside in the graph that the variation of the resistance is quite smooth. Mostly overlapping is taking place of the resistance. X-axis is nothing but the tap positions 1 to 17, and the y-axis is nothing but the resistance itself in milliohms. If you see the table, and different testing kits are having different type of variations. Some may be taking variations from the minimum value of the resistance. Minimum value means which phase is having least value of the resistance, and some may be having variations calculation on the basis of the mean value or average value of the resistance arrived for all the three windings. So that way the deviations or variations are recorded, and accordingly the curves are plotted. So this this is a very important tool to know the also to know the health of the OLTC of the transformer. Then LV side also it is on LV side it is also done. On LV side it is done basically to know if there are some issues with the connections, etc. Otherwise, LV side it is generally very LV side LV side resistance is very small resistance is there, so not much importance is given. Otherwise, if there is some deviations are beyond some acceptable limits, then there may be some issues with the. Sometimes we have seen such cases where the hot spot is there or high resistance has developed between LV bushing and the winding connections. So that kind of issues may be traced through this kind of test if we perform on the LV side also. Next. So generally two types of tests are done nowadays on if we see winding resistance measurements. These are static and dynamic winding resistance measurements. Static measurements means you without any movement, you measure the winding resistance, and it is most commonly done easiest way to check the issues related with the winding and OLTC. It investigates the resistance of each subsequent tap positions and compares it with the reference measurement data, means the data provided by the manufacturer and the test which is performed after at the factory level itself, and also the results are compared with the previous test results. And dynamic resistance measurement is basically nothing but when the tap is in operation, during its operation the current variation will take place, and that current variation is recorded with respect to time, and accordingly by doing this test dynamic resistance measurement, what we know, what kind of problems we arrive is to know is that switching, if there is some issues in the tap changer during switching, or some issues with the resistance itself, that kind of issues may be checked through the dynamic resistance measurement test. Next. So this is the graphical or pictorial indication of the dynamic resistance and transition time of the tap changer. How we know, if you see the curve in on the graph, which indicates position 1, 2, 3, and 4. So 1 is it's when we start tap changing. So before tap changing, the tap will be in position A, which is indicated before tap operation, which is indicated by position 1. So you see that what is the value of the current. Current means the current taken by the motor of the tap changer, that is recorded against time. So when you move the tap from position A to B, intermittent positions are there, which is indicated by position this 1, indication 1, which is being indicated by Bharat. And the during this time, because you see that the R resistance, transition resistance is in two parts, which is indicated in two portions. So first portion of the transition resistance will come in picture with the winding. So drop in the current will take place, which is indicated by the figure as a drop from 1 to 2. And when next position takes place, position 2 indicated just above the graph. So in this position, the two resistance, two half portions of the resistance will be short circuited, and slight increase in the current will take place. And then next position is 3, where again the drop in the current will be seen, because you see the drop in current is taking place because of the resistance is coming in picture during the transition of tap from one position to the other. So when it is reaching to position 3, 1 to 3, the voltage, the current drop was taking place. But in between, when the two R's were in parallel, slight increase has taken place. And again, when the trap is in position 4, final position, when trap change has taken place, the current will increase and will reach to near to its original value. So this way, tap changing procedure is there, and accordingly, the nowadays the test kits which are coming are recording these current variations on the basis of these current variations, the problems or issues in the tap. If there are some issues, those are indicated by this kind of tests, which are indicated again by the this curve, next curve. So as you see, the current variation with respect to time, one of the portion has been enlarged. Okay, next. Next is the capacitance and dissipation factor 10 delta measurement. As you know that another vital testing on the power transformer during field is its testing of its insulation. Insulation, the solid insulation, which is in form of the paper, impregnated paper, and then in form of the insulating oil. And in addition to oil and paper, there are other components like like press boards are also there, other structures are also there. Those are also, when you do this test, so what happens basically, as you know that any capacitor, the two windings and the insulation between the two windings and tank, each and everything, when you inject low frequency voltage or low frequency low voltage signal to the one of the winding or with respect between two windings, so what happens, the two windings or the tank and other components inside take form of a insulator. So as I discussed earlier, that it is not possible that to have any insulator as a pure insulator. There are always some losses inside the insulator. Means in case of transformer, if we see, if we look, if we discuss that what are these the deficiencies, these are in form of they may be in form of contaminations, maybe in form of the moisture ingress inside the oil and paper also. So those kind of impurities or contaminations may cause loss and may affect the life of the insulation. So during its lifetime, the its measurement of the 10 delta is done, and it gives very useful information about the health of the insulation inside the transformer, that what is the condition of the oil, what corrective action is required to be taken, whether we service or we regenerate the oil, or whether we do some induction heating on the transformer to improve its health. So this information may be arrived by doing this test. So as you know that any parallel plate capacitance is defined by epsilon 0 epsilon r a by d. A is the area of the plates and d is the distance. So inversely proportional to the distance. Same principle is applied in this case also. The two windings and insulation is oil and the paper. So what happens that when you do this test, generally we discuss is like power factor and dissipation factor. Two terms are discussed, power factor and dissipation factor. But many times when we discuss these two terms, many times you see that when we reach towards zero value of these factors, both are almost equal. Otherwise, the two are different. One is tan delta and another is cosine. One is tan and another is cosine. Both are indicated here in picture. Tan delta is nothing but the ratio of the resistive components or loss component of the current to the capacitive current. Whenever you charge the capacitor or wherever you inject the voltage to the test sample, what happens? The total current will having low value of very less value of the loss component and high value of the total current. So ratio of the resistive component to the capacitive component of the current is known as the tan delta, whereas the cosine of the loss component to the total current is known as the cosine or the power factor. But the two factor, if the oil is in or the insulation is good health, like that of a new transformer, new oil is there, both the factors may be equal. Okay. So high oil conductivity, ionization, aging, and increase in the water contents, as I discussed, may cause degradation of the insulation and may cause increase in the losses of the transformer. Changes in the capacitance can also indicate partial breakdown or some issues related with the insulation, and even some deformation has taken place, because as we see from the formula itself, capacitance is equal to A by D, epsilon A by D. So if there is a change inside the geometry of the winding, also some displacement has taken place, then again by measurement of the capacitances, this kind of information may be drawn, that whether the transformer is healthy or some issues are there with the transformer. By measuring the capacitance and losses, problem in the insulation can be detected. Not only in insulation, even in during transportation, if something wrong has happened, that may also be indicated through these tests. Means variation in tan delta may happen in that case also. Next.
Respected sir, because of the time limitation, can we move slightly fast?
Okay, sir. Okay. So dissipation factor, as I discussed, basically it is done on the transformer, and we do 5 type of tan delta measurements. The picture indicates capacitance between high voltage and low voltage winding, then capacitance between high voltage to earth, high voltage, low voltage to earth. So CHL, CH, and CL. Okay. Next. What is the significance of the temperature? You see, as I discussed earlier, that because of the variation in temperature, the loss component, losses inside the insulator may change. Every insulator, when subjected to different temperature, will be having different, the resistance will vary. Accordingly, losses will vary. So it is very important that whenever we do tan delta measurement, as I discussed in case of resistance, the tan delta value should also be referred back at the same temperature always. Means whatever values we have taken earlier, if we measure it at different temperature, then should be converted at the same value of the temperature. For that, we are having arrangement in the kits also. So significance of the humidity, if we do it without cleaning of the bushing, etc., or some in humid environment condition, even sometimes we have seen that if we do it in evening, the results may vary. So that kind of precautions may be taken care of while doing this tan delta measurement. Next. And as I discussed, these are the results. 5 measurements we are doing in BSES, in ungrounded specimen test and grounded specimen test and grounded specimen test with guard. So we will discuss sometimes later on in detail each and every test that, but tan delta measurement basically is indicating us about the health of the insulation or any change inside the geometry of the transformer winding or something, something wrong has taken place inside the transformer. Okay, next. So these are the principal diagrams, how we do, how we test different tan delta, and how these values are calculated. For this purpose, the principal diagrams show that how these different tests are done, but the arrangements are there inside the kits itself. Generally, we connect once, and all arrangements, all correct connections are taken automatically by the kit. Generally, the figure which is indicated in this, basically we are connecting the test high voltage test probe on the HV winding, and the response is measured on the LV winding, and accordingly the connections are shifted inside the kit to measure various types of the 10 delta values. Next, these are the curves which we are showing here for different transformers, and the trends. Trends means, as I mentioned earlier, that to know that what are the issues, or whether the contamination or the moisture ingress is taking place. These are basically trends. So it is very important to see how the trends are doing when we measure the 10 delta over the years. See, in this picture, we are showing 2017 to 2019. Even we compare, many times we compare 5-year trends. So what are the variations? As per guidelines, normally on a new transformer, if you look into the different standards, you will see that on a new transformer, the results may be 0.5% initially, and variation is allowed according to age 0.1% per year. So if a transformer 10-year-old transformer is there, then 10 into 0.1 means 1%, and initial value 1.5%, then the 10 delta value may be 1.5%. So accordingly, every testing engineer, by virtue of his or her experience, may see and look into these results. These results are, you see, just like as the doctor is performing ultrasound on a human being to assess to a various health related issues related to maybe even urine related infection, or sometimes abdomen related issues. Similarly, these types of tests are done, diagnostic testings are done on a transformer to know the health of the transformer. Sometimes, especially, we do these tests after some event to know whether something wrong has happened inside the transformer, or otherwise we do as a trend to know the trend, how these parameters are or test results are varying over years, so that different kind of corrective actions should be taken. Next is the capacitance or the DF measurement on the transformer bushing. As just like as the transformer winding health or insulation health assessment, we also do the testing of the 10 delta testing of the bushing. And generally we talk about the C1 and C2 test. You know that the bushing principal diagram is shown. In center it is rod, and outside, to have the grading of the insulation, various foils of the conducting foils are provided in between the insulation, so that to grade the insulation, so that the even distribution of the voltage stress takes place across the all insulation thickness we have provided inside the bushing. So just like as the other I discussed earlier in case of winding and the insulation 10 delta, the 10 delta test is also done on the bushing, and generally we do C1 and C2. C1 is important, and C1 is nothing but the capacitance between the outer layer of the this film. Next slide. C1 is outer paper or outer film, last and inside, and the rod. So C1 is important, and C1 is the indication of the health of the all the means bushing insulation, and C2 is basically about it talks about the outer film and the tab, the tab which we are taking out from the outer film to earth with the tank. Because you know, if you don't earth the outside layer of the film, the grading of the entire insulation will not be even. So outer film of the this foil is grounded, is connected to the earth, and accordingly we measure C1 and C2. In field, many times we ignore C2 because it is just indication of the health of the connection between the outer film, outer layer of the foil, and the connection which is coming out of the foil to ground it. So just to assess its health. So many times we do not refer it, but it is important. Okay, next. So C1, C2 we have discussed. Next, another vital test is the IR, generally done in the field. But you see, if you discuss it in, if you see paper of Mr. Murthy, which in which he discusses about the IS 2026, which do not mention about the this IR test or PI test, basically, but still it gives fair information about the moisture or inside the transformer. Basically, the polarization index or insulation, first is the insulation resistance measurement and then the polarization index. Polarization index is nothing but the ratio of the two insulation resistances, means one resistance taken after 10 minutes and another taken after 1 minute of the measuring. So the two values of the insulation resistances are recorded and ratio is calculated because it is index, so having no unit, and as indicated in the picture, when we do this test, the current which flows through the insulation will be having three component: capacitive charging current, then absorption current, which is also known as the uh, uh, absorption current, and which is also known as the ionization current, means the molecules which are there takes polar form. So polarization current. So in this current is also known as the polarization current or absorption current, and last current is the leakage or conduction current. The three currents, as you see in the graph, when we go after take the reading after 10 minutes, only conduction current will be there. The two currents means capacitive charging current and the absorption current will be will not be there. So that is the significance why we do it after 10 minutes and 1 minute, and ratio is calculated, which gives fair information about the health of the insulation, which is indicated on the next slide. And in another standard is it discusses about the PI also, that how the PI should be there. If it is near 1, then it is questionable. Then if it is 1 to 1.4, it is bad. If it is 1.4 to 1.6, 1.7, we may say it is fair enough, but generally it should be more than 2. If it is more than 1.8, 1.2, then we may say it is good or desirable. Next. Transfer turn ratio is also measured. Basically, ratio measurement are performed to verify whether the are there any issues inside the transformer, some shorted turns are there, or some open circuit is has taken place, or some problems are there with the core, etc. So basically, magnetic circuit and the winding integrity are checked through this test. How it is done? HV winding is given high voltage, and low voltage winding low voltage winding measurement is done and ratio is calculated. The permissive error as mentioned is should be less than 5%. Nowadays, this is done through kit, and kit is having arrangement to show you the complete table, complete result, including ratio as well as the phase angle error, and both errors are combined in the composite error. Earlier days when we were doing these kits were not available, we did simply doing the voltage ratio test. Voltage ratio, that time the phase angle we were not very much, we were not knowing about the phase angle error by doing simple voltage ratio test. But nowadays by doing this test through test kits, even the phase angle errors can be measured. Next. So as I said earlier, that when there are some issues with the transformer, simply the electrical testing may not suffice. Many times we go for the dissolved gas analysis to conclude whether there are some issues. So different kind of gas, sometimes later on we will discuss in detail that what kind of gases are formed inside the transformer if there are some issues. So those gases are measured, and accordingly the results of the DGA are checked in light of the electrical testing, and accordingly the inferences are drawn to check whether some issue has taken place inside the transformer. Maybe what kind of fault is there inside the transformer. Fault is whether with the core, whether with the winding, some copper involvement is there. So different type of faults, different in the different temperature regions. So that kind of informations may be taken or maybe derived out if we see the DGA as well as the electrical tests both simultaneously. So DGA are very important if we want to arrive on the conclusive result, or we want to drive conclusively that what kind of issues have taken place. Next. This is the table which indicates about the key gases, possible faults, and the possible findings. So next, some cases studies are there. I would request Mr. Bharat to just discuss in last few minutes that.
Yes, and the value addition is the case studies, because whenever we talk about some theoretical parts, when we correlate it with the case study, the scenario becomes different. Now the time to talk about the case studies. Please start.
So I stop here, and I will request Mr. Bharat just to discuss.
Mr. Bharat, please start your presentation on the case studies. Thank you.
Good evening, everyone. Now we will discuss a few cases where we could diagnose faults in the transformers based on different tests, and severe damages could be prevented by timely action. So the first case I'm going to discuss is tripping of a 20 MVA power transformer on OLTC PRV protection. So this transformer also had the automatic voltage regulator AVR in service, and when it tripped, we first checked for any kind of pickup in the overcurrent and differential relay, but no pickup was found. Thereafter, we proceeded for the testing of this transformer. Now, when we were testing the winding resistance of this transformer, as per the ideal condition, as per the design of the transformer, when I'm moving from tap number 1 to tap number 17, my winding resistance should decrease linearly. However, what we found was at multiple tap position, there was a sudden rise in the tap on the winding resistance. For example, take this case of the YB phase, which I am showing here. At tap number 2, I was getting 277 milliohms, and when I tested at the tap number 3, it suddenly rose to 812 milliohms. Now we again retested at this particular tap only, tap number 3. The result was consistent, same 812 milliohms. So what we did was we tried to move back and forth on different taps, from tap number 3 to 2, and then coming again back on from 2 to 3. Every time we were noticing that when we are changing the tap, the resistance value is different. So basically the repeatability of resistance values was failed. So thereafter, what we did was we took another winding resistance kit also, and we tried to test with that kit. Again, the same pattern was there. So we were sure that there is some kind of fault definitely there in the transformer. So we went for the inspection of the transformer through inspection window. So what we found was, as you can see in this picture, the Y-phase transition resistance, it was found to be burned. And ideally speaking, this resistance, transition resistance comes into the picture only when we are changing the tap. But we were seeing the effect of it is also there when we are measuring the static resistance. Why it was so was that due to some misalignment in the YB phase, this pole arm, this resistance was not getting disconnected after changing the tap position. So due to which it was also feeding the load current for which it was not designed. And due to this, it got damaged. You can see the strands have got damaged and we were getting an abnormal pattern of winding resistance. So this transformer, this overhauling was done at site only. This resistance was changed and alignment was corrected. And thereafter, we received got proper results. Now coming on to the next case, this is also related to the winding resistance measurement. Test was conducted during the preventive maintenance. As sir discussed previously also that when we are measuring the resistance, we should compare the values face to face also. For example, let's say at tap number 2 here, I will just see the relation, what is the variation of resistance of RY, YB and BR. So what we noticed for this transformer was that for almost all the tap positions, this variation is more than 3%, which was quite abnormal. You can see it from the graph also, the pattern is not uniform. Sometimes we are seeing a rise in resistance also. So it was decided to inspect this transformer OLTC because the kind of variation which is there on all the taps indicate there must be something, some problem with the moving contacts of the transformer. Then only it can happen that all the taps are showing some kind of variations. One of the photo is attached here also. You can see here that on the these connections at the barrier plate also, some kind of carbon deposition is there, which you can see here in almost all the taps. Further, now you can see in last view of these moving contacts, you can see these contacts are also in carbonized condition, and we found that a significant amount of carbon was deposited at base of the tank also due to maybe the continuous arcing of the because of loose contacts. So these moving contacts were cleaned and tightness was ensured, and thereafter transformer taken back into the service. Now come to the next case where a power transformer tripped on differential protection with a very low intensity fault current. This was a 20 MV transformer and its full load current is 350 amperes, and we observed that it tripped on differential for a mere current of 270 amperes. Thereafter, we conducted all the electrical tests on this transformer, its magnetic balance, winding, short circuit, TTR. All the results were found satisfactory. But what difference we found was that during conducting the 10 delta test, when we were measuring the HV to ground results, the 10 delta value increased from 1% to 11% within a span of 6 months. So this was a very significant rise in the 10 delta values. As you can see here, this is the measurement for HV to ground, and this is for HV to ground plus HV to LV. Also, we noticed that capacitance, which should add like this CHL plus CHG should be equal to CHL plus CHG here in the GST mode. This addition was not satisfying. So we planned for inspecting the transformer through the inspection plates, and what was found that the OLTC barrier plate, it was highly carbonized. The chamber was completely carbonized because of some internal arcing, due to which the insulation level was of this transformer suddenly started to decrease. So thereafter, the corrective action was taken. The chamber was cleaned, and the connection tightening was carried out at the barrier plates, and it was re-energized. Now, this case number 4 is quite interesting. This is again about a tripping of a transformer 20 MVA on differential and earthfall protection. In this case also, we received a quite low value of fault currents. See, for this particular 33 by 11 kV transformer, ideally my fault current of 33 kV side is around 10 to 12 kiloamperes, and for 11 kV side it is around 6 to 7 kiloamperes. But what fault currents were recorded during tripping of this transformer on HV side, the currents were merely 560 ampere and 630 amperes, and the B phase was recording simply the load current which was flowing at that time, and neutral current was quite high. Now we compared that what was the voltage profile at that time. So we recorded we captured this voltage profile from the DR of my incoming line. We found that all the phases of voltage R, Y, B, they are symmetrical at 120 degree apart. But the line currents of the transformer R and Y phase, they are in almost same phase, close to zero, and neutral current is exactly opposite and sum of R and Y phase. Now, this was quite an interesting case, because if suppose there is a fault on LV side of the transformer, my current will flow from the HV R and Y phase, and they should be 180-degree out of phase. But here we were getting current which were in same phase. Now intensity of this current is also very low. So any kind, I know that my bus fault here, if some bus fault occurs here outside the transformer, the current is going to be of order of somewhere around 10 to 12 kiloamperes. But I'm just getting a 580 ampere currents. So we understood that there is no any fault which is outside the transformer. There must be something within the transformer which is creating a problem. So electrical tests of this transformer was carried out, and all electrical test results were found satisfactory. Be it GST, that 10 delta values, WRM short circuit, everything was fine. However, when we conducted the DG of this transformer and compared with the last year values, there was a significant rise in acetylene content in this transformer. So this acetylene formation indicated that some internal arcing is there in the transformer. So it was decided to drain the transformer oil and inspect from the inspection window. So from the top, we couldn't find anything. Thereafter, that oil was completely drained. And from the bottom window, what we found was, see, in transformer, apart from the HV main winding, this HV main winding, we have got some tappings. These tappings are coming from the transformer main HV winding in form of leads and going into the OLTC chamber. Now for particular 17th number, this lead of our phase, we found that its insulation was damaged at near the OLTC chamber point only, and some pitting was also found on the tank. I will show in next slide. See, this is the lead number 17 from the R phase winding. We saw that you can see here there was some kind of a spark here, and its insulation was damaged. Also, when we looked at the place where it was resting at this place only, and here we saw that there was some splitting here. But because when the transformer was in de-energized condition, there were no vibrations. These were not exactly touching here at that time, and on all our electrical tests, everything passed because there was not direct connection. However, when the transformer was in energized condition, maybe due to the vibrations in the transformer, it was touching here and transformer tripped. So thereafter, this insulation was repaired and this fitting was also repaired, and the transformer was energized again. So in transformers, we saw in the very first slide, we have got different components. There is core, there is winding, insulation, multiple things are there. Now, when I say that my winding is healthy, to a certain days, there is not only based on one test I can say that my winding is healthy. I have to perform a number of tests to be sure that my winding is healthy. Similarly, if we look at the overall complete transformer, we have to do so many tests, we have to analyze so many reports at the same time to ascertain whether my transformer is healthy or not. Otherwise, we may lose any importance of one particular test. So from there arises the concept of transformer health index. Basically, what we are doing here is empirically, we are collecting all the results and evaluating them as based on whether they are good or not. We are bringing all the essential results like 10 delta, winding resistance, the transition time of the OLTCs, the quality of oil, its GGA, PI values. We are bringing under one window and we are giving it a diagnostic index here. When its quality is best, we are saying it is value 4. When its quality is worst, we are saying its value is 0. And based on that, we are calculating the health index, which clearly gives me interpretation of combined all the results, whether this transformer is healthy or it needs some attention or it has gone unhealthy. So this is the need of our now when we are talking about comprehensive testing of the complete transformer. So thank you, sir. This was all from my side.
Okay, mind-blowing, wonderful, insightful presentation from Umesh sir and Bharatji. Thank you once again. Before I go for the question, I would like to invite respected spouse sir. Kindly unmute yourself and say a few words before I take questions. Sakesh ji, please unmute. Apao sir.
Yes, yes. Good evening, Rajaji. Thank you for your kind arrangement for this webinar. Actually, transformer being heart of every electrical installation is a vital webinar. Mr. Umesh Gupta, as well as the especially the case study by Bharat, are quite enthralling. It's very good. The presenter has aptly devised the timing. Of course, this is not sufficient for them to cover all the areas. Anyhow, they have touched upon this systematic way on the presentation. Necessity of tests, various tests, including the method of connection and typical values. I think they have put everything in a transparent manner so that there is no secrecy. I should appreciate them for such a wonderful webinar. And thank you, Mr. Rajaji, to come up with it.
Thank you. Thank you. Now, I would like to request the participant, they can unmute one by one and ask the question.
Hello.
Yes,
Sir,
please.
hello.
Yes, please.
Hello. Sir, Lavneet here, sir. Good evening, all. Sir, now we are using this ester oil instead of mineral oil. So, what is the frequency of checking that dehydration and BDB for ester oil?
So if you if you look into this as I discussed earlier, for this I would request you to just go through the C57-152 2013 standard. It talks about the various various insulating fluids used inside the transformer, and what kind of means that at what frequency we should perform different tests on these kind of insulating media. Okay.
Next question. Kindly unmute yourself.
Because you see, in this presentation, we have generally discussed about the power transformers which are using mineral oil as insulating media and cooling media. But if you want to know about the other materials like ester oil, etc., I would request you to study in detail C57-152 2013, which has discussed in detail different types of insulating and cooling media, and what kind of tests and checks should be performed and at what intervals.
Apart from that, you can also refer IEEE C57-12-90 2016. That
Yes.
can be referred.
Yes.
Hello, sir. This is Anas Adhikari.
Yes, Adhikari ji, welcome to the show and please ask your question.
Thank you, sir. Thank you. It was a very nice presentation. I would like, sir, in one of your slides, you mentioned that the permissible 10 delta, that variation in 10 delta value is 0.1% per year, or that is 3% whole, whichever is lesser.
3% is the final value. Generally, we do maintenance, or we recommend our operation and maintenance department to do treatment of the oil or the winding if we see that the absolute value has gone above 3%, or the trends, or if the trends are beyond permissible limits, that 0.1% per year. Suddenly, if there are changes abruptly, say if in a particular year the 10 delta value is say 0.8%, and next year if we measure if it is 1.5%, so sudden increase of 7% means almost double. So in that case we have to look into further that what kind of problem has taken place inside the transformer.
Sir, I would like to know the name of the standards in which it is written.
Both the standards we were discussing, it is mentioned IEEE C57-152 2013, and the one which Dr. Rajesh is talking about.
IEEE C57-12-90.
And also IS
I think I
2026.
have gone through it, but I didn't find it that it is written in terms of 10 delta value. In terms of bushing, it is written, but not in terms of winding.
I think somewhere you have missed. Otherwise, just before this presentation, I was studying that, wherein it is mentioned at one place it should be 0.5%, and variation is also mentioned in the table. And
0.5% that is for the capacitance value, I think, sir.
uh,
Bushing, in case of bushing,
I
RIP
think
bushing.
What I will do, I will share that particular snapshot with you.
Okay, sir.
Don't
Okay.
worry.
Thank you, sir.
Otherwise,
Thank
we
you.
will discuss one-to-one. We can move to the next question.
Thank you, sir. Thank you so much.
Don't worry, we will answer it.
Okay.
Next question.
Rajeshi, I am NK Mittal. My next question is, many times, although the Mr. Bharat has explained very well, whenever there is a tripping on REF or differential, most likely reason is either open transition, or that plate on the backside of the OLTC is faulty, or that one of the resistance is going up, or 10 delta is going up. But many times what we have seen is, we have seen the tripping, and we just allow 5 or 10 minutes to see that what is the fault, and we put it on, and then it is normal. Number one. Number two, many times we have seen the transformer tripping on buckles working on a, no, I'm not talking of power transformer, I'm talking of distribution transformer. It's working perfectly well. All of a sudden there is a tripping on buckles, and you wait for maybe 30 minutes or so, you put it on, and again it is working. You see after 1 month, 1.5 months, again it trips on buckles. Again, you wait for about 30 minutes, and it is back to normal maybe for a year. So what is this kind of a transition that happens in the buckles?
so,
Sir, I would like to answer that question because when you talk about the generation of gases in the transformer, that is because of some arcing or some thermal effect. What happens, the gases generated in the transformer depends on the type of fault and the temperature associated with that gases. Okay. And when you are saying sometimes the gases are coming, sometimes gases are not coming, that depends on the fault. That already given in the very beautiful case study number 4. At the time of load, that was touching, and when it was not on load, that was not touching. Such cases usually happens when that arcing becomes, you can say, solid. That is not a fault. That start conducting in a proper way. Initially, when the of arcing start, their temperature rises like anything. It may be more than 700, 800. At that point of time, the buckles may strip. After some time, when that arcing, that fault becomes solid, that generation of gases may not be there. And it may run for many years, and after some year again, the problems start again. I have seen, this is my practical thing.
I have seen
Mittal
it
sahab,
repeatedly.
Rajeshi, shall I supplement also something?
Please.
In few cases, Mittal sahab, we have seen different kind of thing also. In some cases where the transformer is having age more than say 10, 12, 20 years, or it is quite old, it has been seen that some damage on the core insulation has taken place, and because of the moisture inside the transformer, the local heating of the core is taking place, and because of that local heating of the core, oxidation or some gases formation takes place. Maybe it may be hydrogen or something else that flows out of that transformer and comes to the bucause. So quite few times we have seen few cases. In those cases, the transformer has tripped because of this kind of reason. But because the electrical circuit is healthy, no fault inside the winding, etc., the transformer was put back into operation after removing the gas, or even sometimes just by keeping it off for certain time. as you discussed.
Yes,
So
very
that
true,
kind,
very true,
that kind of experiences are also there in field.
very true.
So that those cases may be there in that case.
So,
For the earlier person who was asking about the 10 delta, I would like to refer clause number 5.1 of C57 152 2013, wherein the table is there and the 10 delta recommended delta values are mentioned and its
Yes.
variation are there. Clause number 5.1.
5.1 you can refer, Adhikari sir.
sir, how important is the 10 delta test for particularly distribution transformer up to 2500 kVA?
Basically, in this presentation, we were talking about the power transformer. Exactly, we have not done these kind of testing on the distribution transformers of 1000 or as you are discussing to 2500 kVA. But I hope the principle also applies there. And if you test those distribution transformers, similar kind of results will be there.
Okay.
Sir, for distribution transformer, the latest IS is 1180, and in that IS you can see they have given emphasis on the 10 delta value.
Is it for the bushing or is it for the winding?
It is for the bind. It is the 1180 is for distribution transformer.
Okay. So we should be measuring it regularly in that case, maybe on a yearly basis.
Yeah, at least once in a year that should be measured.
And we should ask the manufacturer to declare it at the time of.
Yes, at the time of manufacturing, the
test.
value should be taken and that should be taken as a reference for the future testing.
Okay.
Next question. I think if there is no question, I should say thank you to the presenter, Umesh sir. Thank you very much for sharing that insightful, wonderful presentation and sparing your valuable time. At the same time, thank you to Bharat for giving wonderful case studies or case studies that was in fact very insightful. With that, I would like to say thank you to everyone for sparing your invaluable time. Thank you, sir. Thank you very much.
Thank you, Dr. Rajesh, and all the participants who have spared their valuable time with us. Thank you.
Thank
And it's not an end, just we have tried to sensitize and make aware. If you want to learn further, I would request you just to study these standards and other books on the power transfer testing.
Yes, if required, we can go with the second part of that presentation also. Thank you. Thank you, everyone. Thanks a lot.